Hey everyone, and yeah, welcome back to the session. So before we begin, just wanted to ask if you're all able to hear me properly and see the screen. You can just let me know so we can go ahead. Right, perfect. Thanks for letting me know. So we can move ahead from where we left off. All right. So moving along from the basics of looping constructs, we're going to move ahead to a various set of operators that we're going to learn to use and learn to work with. But prior to that, one thing that we should know with respect to strings is that when we talk about strings, given any string that you use is an object of the class called string. This class has a series of functions that you can use. So for any string that you create, like hello, for instance, you can use this string with some functions like, for instance, capitalize. Capitalize will make sure that the first letter is capitalized, or it could be to uppercase, where entire string is converted to uppercase. It could be entire string converted to lowercase. It could be to trim spaces. For instance, somebody might have typed an email ID with some space ahead. They might have just copied and pasted it, right? Like a@gmail.com, followed by one or two spaces. These spaces will be uh, copied as well by default. Now, at that particular point of time, when these spaces are also copied by default, you want to remove these spaces ahead and before. That is prefix and suffix of the string, and only copy the string. Then you can trim it. So there are a lot of these inbuilt functions that are available within strings that you can utilize. Just for our understanding, for a simple example, you can take, let's say, s1 equals space hello and then space. I'm just going to write s1 dot strip. Strip is a function that will remove leading and trailing white space. That is, if there are any spaces before the first character and any spaces after the last character, these spaces will be removed. And that's exactly what this function does. And one thing that we need to know about strings in Python is that certain data structures or certain data types within Python are immutable, which essentially means that you cannot change them ever. They can never change. They are always constant based on this. What this means, in other words, is whenever you perform some operations on, let's say, strings, for example, if you modify a string, just think about this. If we modify a string, that modified string will be in a different memory, will be in a different memory location. It will not be in the same memory location. So let me just walk through what I mean by this so we can understand this better. Now, if I perform any modification to a string, let's say we have a string called s1, which is hello, for instance. Now, if I modify this, let's say s1 dot strip, what this does is it tries to remove these trailing and leading white spaces in s1. However, the problem here is this. When we remove these trailing and leading white spaces in S1, we cannot, in other words, store it back in the original string that we had. We cannot store the result back in the exact string that we had. It's not going to modify S1 because strings are immutable. If S1 is storing some spaces and hello and some spaces in a memory location of 920, and when you perform s1.strip, it's going to create a new string. Let's call it s2 for our understanding, which is going to be hello without any spaces anywhere. And it's going to store it in some other location like 960. And it's going to return this location back as a new string. So whenever you perform functions that replace, that modify a string, always remember that function will return a new string which you can store back in S1 or anywhere you want. But just remember it returns a new copy of the string because strings cannot be modified. So you cannot just say, I'm just going to perform s1.strip and it'll modify s1. You have to perform s1.strip, followed by which you have to then take it up as s1.strip response would be stored in some string or somewhere. So let's try to take a look at this. Let's store it in s1. There we go. Let's run this. You can, okay, let me print s1. Prior to this, let me just not do this, and I'll directly print s1 to show the difference. You can still see there is spaces prior to and ahead of hello. However, ahead we really won't get to know, but I hope you get the point regardless. So instead of that, I'm just gonna store the result somewhere, and let's try it again. Now you get hello exactly as expected. So this is one thing that we need to know and understand when it comes down to strings, particularly because strings are immutable. We cannot change the value of a string at all. It has to be, in other words, stored in a different variable whenever you perform any modification to it. That's just one thing that we need to know about strings. Anyway, let's move away from that and let's move on to the next case. There are a lot of other functions, but again, given the interest of time that we have pretty much 40 hours or 5 days of sessions, I will not be going through every single function, but I would highly request and recommend you go through some functions. Just type s1 dot and take a look at all the functions here. The advantage for us to figure out here is that all the functions would start with these purple cubes, and all the variables will start with these boxes with these square brackets around them. So if it's a variable, it's going to start with this. If it's a function, it's going to start with these purple cube. So anything that you want to know, just click on it, add brackets. You'll get to know what it does, what it returns, how it works. This is a really nice way to understand and look at, let's say, various functions and strings and see how they work, see how they perform their operation, understand their inner workings, and so on. So it's something that I would highly suggest um, everyone to just go through. Though, regardless, we might not use it on an everyday basis. It's at least useful to know it once to begin with. But yeah, anyway, moving ahead, the main point I wanted to make was to show that strings are immutable, and any operation that you do on top of strings, it returns a new string that you have to store somewhere else. And that's the whole idea or purpose of working with strings here. Now, with this idea, let's now move ahead over to the next part of this. Right. The next thing we're going to start to look at if you want to look at all these, let's say, operators and work around them, the first thing we're going to take a look at is how to work around data structures first. We're not going to start with these operators directly without data structures because all of these will be much easier by learning different data structures. So the first thing we'll do is just create a new file. Let's start with data structures.py. All right, now I have one question before we start with data structures. I just want us to think of this. Let's just think of this in short. If I have an array or an iterable or a list of certain elements like 1, 2, 3, 4, up to 10, and I want to search for a particular element within this list of elements. I want to search for one element. It could be any element. I might search for 1, I might search for 10, I might search for 5, I might even search for 56. I might search for any element. Now, my question is pretty simple. What is the minimum number of steps that I can take to search for any element? You can unmute and speak about this if you would like to just have a discussion on this. My question is pretty simple. What would be the best approach for you to search an element? That is, what would be the best approach to search an element in such a way that your search happens in the fastest possible time? So, any of you can think of whatever you think is the best approach to search for an element. And yeah, you can let me know. We can take a look at what is that approach and how are we working around it. All right. So let me start with some baseline for our understanding because I know I'm asking a query that might be something that some of you might have gone through, some of you might not have gone through. It's just a thought process that we are looking for. One way for me to search any element is one element at a time. If I want to search for any element, I'll go through each and every element. That is, in this case, if I want to search for an element, let's say 56, I'll go through the entire list from left to right. Is the first one 56? Is the next one? Or the next? And so on. Until we reach the end of the list. Until we have searched every single element. This will give us about 10 searches. So for a list of 10 elements, I have to search 10 times to figure out whether an element is there or not. This is in the worst case. Worst case, assuming that that particular element does not exist at all. We are assuming in such a case scenario. Now, on the other hand, let's think about this. Do you think there might be any better ways to search these elements? Let's take 56 for example. Do you think there might be a better way to search this element?
Well, I know on a SQL table, you'd set up indexes. So you're not searching the whole array, you're searching chunks at a time.
Perfect. So when we compare it with respect to databases, absolutely right. One way to work around it is to make sure that we have oh, sorry, we can't say indices over there, indexes rather. But yeah, that makes perfect sense. But in that case, index would be 1, 2, 3, 4, 5. Let's say we have something like this. We have indexes 1, 2, 3, 4, 5, 6, and so on. For the index 1, you'll have a value 1. For the index 2, you'll have a value 2. For index 3, you'll have 3. For index 4, you'll have 4, and so on. So if you want to search for some index 56, you're going to search whether that exists or not. If that index doesn't exist, you're not going to search for the value. Now, in a bird's eye view, this might seem like, hey, it's the same process, but we have doubled the time. Not exactly. This is much faster because when we talk about indexes, maybe in SQL or so on, not every database, but some databases use indexes as hashes. In other words, what they do is they create a separate array from a given array. So I will not exactly link this to a database now because it differs slightly when we compare to that. So I'm just going to try to work around in a slightly different way to understand this. So let's take a look at this. For instance, let's say we have an array of 10, 20, 30, and 100. Or rather, let's take 50 for instance. Yeah, to make it diverse in this case. So let's consider this. Now, the scenario here is previously. Again, this is where I'm going to start getting into time complexity in a little more detail when we start working on this. The idea of time complexity is that whenever we perform any operation, there's this website that I would highly suggest anybody to take a look at if you want to know about it. There's this website called bigocheatsheet.com. You can find the time complexity of any and every data structure within it. And time complexity, just for us who don't know it, it's just a way to say how much time or how many steps are we spending to perform each operation. Like for example, here, if I want to find an element, if I want to find 56, I'm searching for the first, second, third, fourth, and fifth element. After finding all five elements, I know that it doesn't exist. So I say 56 doesn't exist here. So I've performed five search operations, search with this, and this, in order to make sure that this element doesn't exist. So we say the worst time complexity here, given this array is of length n, is I need to perform n searches. Hence, the worst time complexity is identified by big O of n. Those with prior programming knowledge, particularly in time complexity, who might have gone through this, would know this well enough already. But I'm just walking through this in short, just so we know. In case of big O of n, we get to know the time complexity here is n in worst case. So if there are n elements, if an element doesn't exist and I'm searching it in the array, I need n steps. However, you can do this only in one step as well. This is where programming really helps. This is where a lot of programming really helps us in many cases. So if you take a look at this, the way some data structures work is when you create an array of these elements, it will create a separate hash table. Hash table is basically done by performing some mathematical operations like modulus, for instance. Looking at these numbers, I'll just give you a simple example of modulus for this. I can perform mod 10. 10 mod 10, I'll get 1. So in index 1, I'll place 10. 20 mod 10, I'll get 2. So in index 2, I'll do one little thing. There we go. Yeah. So in index 0, let's ignore, we have nothing. 10 mod 10, I'll get 1. So in index 1, I'll store 10. 20 mod 10, I'll get 2. So in index 2, I'll store 20. Or sorry, not mod. Let's just divide. Yeah. 30 divided by 10, I'll get 3. So in index 3, I'll store 30. 41 by 10, I'll get 4. Let's ignore the remainder. I'll store 41 here. 50 by 10, I'll get 5. Let's store 50 in index 5. Now, if anybody wants to search for element 41, all that I'll do is, if I want to search element 41, I'm just going to perform 41 divided by 10. I'm going to get 4. Ignore the remainder. I'll go to index 4. I'll check if the value present over there is 41. If the value present there is 41, I'm going to say yes, it is present. That's it. So given an array, the approach is to create this other array in which you can find indices based on some operations like this. And this is called hashing. I'm only going through a bird's eye view of hashing, just a basic understanding of it, but you get the idea of how useful it is, right? Let's say if you want to search for 44, again, same logic. 44 divided by 10, you'll get 4. Go to index 4. Do you have 44 in index 4? No. So you can say this element does not exist. Pretty much it. Now comes the problem. Of course, the simplest advantage here is that you can perform any search with just one operation. Even if your array has 1,000 elements, it doesn't make a difference. You just have to perform one mathematical operation. And after that mathematical operation, you need to perform one comparison. So technically, there are two operations. One is for mathematical operation, the other is for comparison. But it's so close to one, we basically call it as big O of one, or worst time complexity of one. And the reason why I'm saying this is where data structures shine. This is why it's important for us to actually learn data structures. That's because In our case, whenever you want to work on any data structure whatsoever, you need to know which data structure works better with what kind of operation. If you're performing search-based operations, there are data structures with hash logic like we just saw, which can perform search in one step. Imagine there's a library. Within a library, you might have 10,000 books, and you want to search for a particular book, whether it exists or not. If you look at the simple linear search scenario like we did earlier, you need to perform 10,000 hits, 10,000 searches. This is going to be very complex and difficult. Instead, you can just directly perform this with just one search as long as they are hashed. So you can see that search time complexity is so low. It becomes so small. You can perform search operations very quickly and easily. However, it comes with a catch. Assume you need to add one more element 44 to this array. If you add 44 to this array, 44 by 10 will also give you 4. And 4 already has one element. You cannot add one more element in that index. You have to make sure that each index has only one element. This insertion, when you insert an element, you'll run into this problem where you cannot insert another element in the same index. This is called hash collision. To avoid hash collision, you have to redo your entire logic. Instead of dividing by 10, you have to find a new logic now. And you have to redo this entire array. That is the difficult part when it comes down to hashing based data structures. Searching is easy, but inserting and deleting elements is going to be complicated because you're going to have to possibly redo your entire hash structure. And this is where understanding data structures is quite important for us because we need to know which data structure to use where. And that is the whole purpose of using data structures to understand their time complexities, like how fast they work, and where to use which one. Where, if I'm performing search, which data structures should I use? If I'm performing only insert and delete more, which data structure to use, and so on. This is where it becomes quite important. And a lot of programmers do not observe and understand this in detail. And I'll just point this out in one simple example, just for our reference and our understanding. The reason why I focus a lot on data structures is, again, back to efficiency. I am a programmer and a developer who works on large scale applications, and many of us might just need to do that sometime in the future, where you need to work either on huge amount of data or you need to work in applications that require huge amount of users using certain applications. In both of these cases, making sure that you're able to perform operations in the shortest time span possible helps a lot. And I've seen a lot of interview candidates over time. I've interviewed a lot of Python developers, particularly, for instance, and Java developers and so on, where they're good at the basics, they're good at understanding the programming language. But whenever we go in depth into utilizing data structures and algorithms in the right way, they often fail. So programming knowledge alone um, does not make us efficient programmers, unfortunately. We need to take a look at data structures and algorithms in detail a lot of times as well. So looking into this particularly, looking into this specifically, let's go ahead and try to understand this and work around this in greater detail. I have one question. Um, so, okay, I'm so sorry, James. I did not observe this because I know you've pasted it now, but somehow I did not get a ping in my earphones for a message. So, to all the participants, in case I did not respond immediately, please let me know. So Yeah, I can respond to that and work around that accordingly. That's something we can do. So yeah, back to the question. Do you have any book, website, or YouTube recommendations to learn more about data structures? Okay, there are a couple of things that I would highly suggest when you work on data structures. Okay, I'll just take a few minutes to walk through this. Again, this is purely my approach, and it might differ from somebody else's approach, just so we understand, because let's face it, everybody might not have the same approach to learn it, right? Um, so my approach goes something like this. It depends on which programming language you want to learn data structures in, because all programming languages won't have data structures in the same way. In Python, I might have hashes based on dictionary or set. In Java, you have something based on a hash map, for example. So it purely depends on what programming language you want to work on. And this is the easier way. I prefer the easier route because it takes lesser time, obviously. So, yeah. My first suggestion would always be to figure out which programming language you're working on and learn all the data structures and time complexity of that programming language. So if I'm going through Python, I would just go online, search for Python data structures and time complexity, something like this. You'll find a lot of these fairly quickly. It should not be difficult. So you can just take a look at this. Let's say for each one, you can immediately find out what are the worst case and best case time complexities. Again, this you can do given you have already got an understanding of time complexity, given you already know time complexity well. And there's one reason why I would never suggest particular books, because each one of us has a different approach of studying. I might prefer a book that goes very in depth and detailed way, which is too technical, but you might, let's say, reach out for a book that has good analogies to explain and understand. So that might differ between us, but the basic idea remains the same. The first step is understanding time complexities. What does n mean? What does n into log n mean? What does just log n mean and everything? If you'd like us to go through in greater detail about time complexity, we can spend maybe at least 10-15 minutes to work around that. Would you all prefer that? To begin with, you can let me know if you would prefer that. We can just walk through a little more in detail about it. So your data structures ideas will be much more stronger when we get into this. Or if you feel time complexity, just the basic idea of it is enough, we can move ahead from there as well.
I would say just carry on with the planned stuff you were going to talk
Uh-huh.
about. I was just asking that question, just I was curious if you had any resources that might not
Perfect.
be, how do I say, like, not well known. Like if you have studied data structures for a while, there might be something that you found like a resource for that's like, hey, maybe not a lot of people know about this specific resource that I think is